All right, let's continue some further examples of differentiation. Here we have the derivative of cosecant times sine. Now, of course, I could do a rather silly thing and go, all right, well, that's minus cosecant x cotangent x, all right, times sine of x, plus cosecant cosine x by the product rule, right? And let's see here, cosecant, how's this go? Well, that's equal to cosecant of x times what? Let's see here, cotangent times sine. Well, remember, cotangent is what? It's cosine over sine, so this is actually just cosine of x. So what you got here is cosecant of x times minus cosine of x plus cosine of x, otherwise known as 0. Of course, this is really not surprising since this is nothing more than 1, right? So of course the derivative is 0. Now, that's mostly true, but it should be qualified. I mean, if I'm going to be pickier, and I haven't been generically that picky through these examples, but to be careful, I should really qualify this and say that that's only true for x not an element of n pi. Well, excuse me, not, sorry, I'm language. In other words, for x not equal to n pi for some n in the integers, right? This isn't even defined there because the cosecant function has divergence. It's not defined integer multiples of pi because it's got it's 1 over sine, right? Division by 0 there. All right, moving on. All right, so next example here, we have the derivative of the exponential composed with the squared function. So the derivative of the exponential is just the exponential function again. And then I have to do d theta of the inside function, which is theta squared. And so there you go, 2 theta e to the theta squared. Or as I prefer to write this, 2 theta exponential of theta squared. I think that's maybe a clearer. These kinds of stacked exponentials are dangerous, and I mean, I think the reader is more inclined to have the right idea from that expression. All right, next one here. Derivative with respect to beta of sine of cosine of beta. So the outside function sine, so that differentiates to cosine. So I've got cosine of cosine beta, right? But then I have to multiply by the derivative with respect to beta of the inside function, right? Of course, this is minus sine beta, and then for reasons of style, I put that at the start of it. It's here. So minus sine beta, cosine of cosine of beta. All right. Let's see here. Moving along, another example. We have the derivative of the square root of 4 plus 3 times the square root of x. The outside function here is square root, right? So I'll put an in-between step for this one. Let's call that whole thing u. So what we're looking at is 1 over 2 times the square root of u times du dx, right? So I'll leave it as u, saves me some writing. 2 square root of u. And then I have d dx of what? d dx of 4 plus 3 times the square root of x. All right, and then I'll write the answer. So this is 1 over 2 times the square root of 4 plus 3 square root of x times what? Times derivative of 4 is 0, right? 4 doesn't change. 3 pulls out of the derivative. The derivative of the square root is 1 over twice the square root. So what I have then is, of course, just 3 over 2 square root of x from the derivative of the inside function. And there you go. Now I suppose we could simplify this one a little bit if we wanted to. I guess I want to. Let me do it. So this is equal to 3, let's see here, 3 divided by 4. I'll bring the 2 out front, and then I've got the square root of what? X plus some bringing the multiplying the square root of x in here. Oop, forgot my 4. So 4x plus, curse is still wrong. Let's see. So sorry. All right, so 3 over 4 times the square root of 4 square root x plus 3 square root of x times square root of x, which is just 3x. So I guess that's simpler. I don't know. Anyway, that is another way to write that. Okay, moving on to my next example. Cosine squared of v squared. All right, so you know what this means. This is really d dv of the cosine of v squared squared. That's what that notation means, right? And so what that is then is 2 cosine of v squared, right? Because that's the inside cosine of v squared. But then I have to multiply by the derivative of the inside function again, which is minus sine of v squared. But then the inside function is still v squared, so I still have to multiply by 2v. Oh, poor planning on my part. Sorry about that. Alright, so cleaning things up a bit, we have minus 2. Oh, I just can't do anything right at the moment. Alright, so minus 4v, 2 times 2 is 4, right? Sine of v squared, cosine of v squared. Let's see here. Yeah. Alright, and there you have it. Let's see here, next example. Move it up here a bit. Come on. Here we have, wow, this one's kind of a doozy. So I'm going to call this thing u, so I don't have to keep writing it a bunch of times. I have u to the 1/3 power, right? Which is 1/3 u to the minus, 1/3 minus 1 is minus 2/3, right? And then I have to do what? I have to multiply that by the derivative of du dx. What is the derivative of du dx? Well, it's d dx of x e to the x, right? Plus d dx, using linearity of the derivative of the hyperbolic sine composed with the 2x function inside. Alright, so what do I got? I've got 1/3 u to the minus 2/3. This is a product, I need the product rule. E to the x plus x e to the x. And this is a composite, so I need the chain rule. Plus 2 cosh 2x. The 2 coming from the chain rule. Right? And then the finishing blow. Alright, so we've got e to the x plus x e to the x. Of course I could have factored the e to the x out, I just chose not to. Plus 2 hyperbolic cosine of 2x. Divided by 3 times parentheses x e to the x plus the hyperbolic sine of 2x, all to the 2/3 power. Minus 2/3 became plus 2/3 because I moved it to the denominator. And there you go. There's another example. Sorry if these are boring, but you need to be really good at differentiation, all right? So I'll just keep doing examples for a while. Now, of course, I can do examples all day long, but unless you actually understand how to do these examples for yourself, you know, it's kind of pointless. So I'm just trying to give you a sense of what you should be able to do, kind of the speed you ought to be able to do it at. Honestly, I'm still going slightly slow. All right, so this is cosine cubed, so the outside function is the cube function. So I have 3 cosine squared x over x plus 1, right? Times what? Times the derivative of the inside function. So then I have to do times d dx of cosine of x over x plus 1, because this was the cube function composed with the cosine of x over that quotient. So then that gives me 3 cosine squared over x times x over x plus 1 times minus sine of x over x plus 1, right? times the derivative with respect to x of the inside function, which in this case is, you guessed it, x over x plus 1. Sidebar, well, not exactly sidebar, but let me just go up in here and say that this piece right here, right, differentiates to what? 1 times x plus 1 minus 1 times x divided by x plus 1 squared by the quotient rule. So I'll use that to write the final answer. Oh man, oh no. I should have. Alright, well, I'll have to do some creative moving here. Equals. Alright, so what we got is minus 3 cosine squared x over x plus 1 sine of x over x plus 1. Let's see here, all divided by x plus 1 quantity squared. And let's see here, what's to simplify? This is x plus 1 minus x, otherwise known as 1. Oh, that's the answer. So, so there you have it. Oh, that's kind of cool. By the way, another way we could, before I get to the next one, just a little sidebar here. It's kind of cool what just happened. X over x plus 1, right, is equal to x plus 1 minus 1 over x plus 1, right? Just adding 0, which is 1 minus 1 over x plus 1, right? So of course the derivative of this is what? See what this is? This simplifies to just 1 over x plus 1 squared. Quite clearly the derivative of this is 1 over x plus 1 squared, because the derivative of the reciprocal function is minus 1 over the square, and there's a minus here, so that's why we ended up with this just multiplication by 1 over x plus 1 squared up here. Anyway, just kind of an interesting comment there. Moving on to the next. Oops, let's not get too far ahead of ourselves. Alright, no time to mess around on this one. Let me put this... so this is... when you see something with natural log of a quotient or something like that, right? What you want to do is you want to use properties of the log before you differentiate. All right. So this is really d dx of what? It's the derivative of the natural log of 1 plus x squared plus the natural log of 1 plus x, minus rather. Man, I gotta find my eraser. 1 plus x to the 4th. All right. Now, there's no fine print here either, because both of the denominator and the numerator here are clearly larger than 1, or at smallest 1, so the natural logs of these quantities make sense. You might find a situation where you had like a natural log of a quotient, like natural log of a over b. You can only simplify it to natural log of a minus natural log of b if you know that a and b are both non-negative, right? You can't take natural log of a negative number, so it's something to watch out for. Alright, anyway, differentiate this, chain rule, 2x over 1 plus x squared minus 4x cubed divided by 1 plus x to the 4th. The 2x and the 4x cubed come from the derivative of the inside function. 1 plus x squared has derivative 2x. 1 plus x to the 4th has derivative 4x cubed. So, there you go. Our next example, here I have a unknown function h. So we're assuming that h is a differentiable. I'm trying to write an h here. H is a function which has a derivative of y which exists, but that's about all we know. All right. So the answer is going to contain h and its derivative. Derivative with respect to y. So what I get is 2y, right, times h plus y squared times dh dy. And that's it. That's as far as we can go. The answer will be in terms of the unknown h, and this, this can happen. All right. Next example. The derivative with respect to theta of sine of tangent of 3 theta. All right, so the outside function sine. So what we got is we got ourselves a cosine, right, of the tangent of 3 theta times e to the theta. And then I have to multiply by the derivative, right, with respect to theta of the tangent of 3 theta times e to the theta, like so. And so, what is that? Well, that's a product, so I need the product rule. And so what I got is I've got cosine of the tangent of 3 theta times e to the theta times, well, let's see here, derivative of tangent theta gives me secant squared 3 theta, but the 3 theta requires multiplication by 3. So what I get is I get 3 secant squared of 3 theta e to the theta plus tangent of 3 theta e to the theta by the product rule. And that is it. So there is the answer. I don't think there's much point in trying to simplify it further. You could factor out an e to the theta. In fact, you have 2 of them, so you have an e to the 2 theta out front. If you wanted to factor that out, you could do that. All right, so our next example. Hey guys, could you please try to keep it quiet in here? Thanks. So here we have the derivative with respect to x of the sinh of the natural log of x. So one way we could go here would just be, okay, well that's cosh. Cosh of the natural log of x. Right? Then the derivative of the inside function is 1 over x, because derivative of natural log is 1 over x, right? And now if I said to simplify answer, I wouldn't be happy with this, right? Because this can be simplified. How can it be simplified? Well, that's 1 over 2x, right? And then e to the, there's a 2 in the definition of cosh, so I have e to the natural log of x plus e to the minus natural log of x, right? And so what that is 1 over 2x, right? Well, that's x, right? And this, well, is plus e to the natural log of x to the minus 1 by the properties of logs, right? But that is 1 over 2x times x plus x to the minus 1, right? Which, of course, we could rewrite as simply 1/2 of 1 plus 1 over x squared. There you go. That's the simplified answer. Now, of course, there's another way you could have done this problem. I'm sorry, I was off the screen a bit there. Let me scooch it up a bit. There we go. Scooch, scooch. This, of course, could also be written as 1/2 e to the natural log of x minus e to the minus natural log of x by the definition of sinh, right? And so this is really just nothing more than 1/2 of x minus 1 over x in disguise, right? And quite clearly, if you differentiate that, you get right to our final answer, right? So, you know, sometimes it's better to make the algebra simplification before, if you can. You got to know our basic definitions in our algebra. Well, I think that's about all I got for just examples of just plain differentiation. Our next topic will be implicit differentiation. Thanks, guys.